Hello to one and all present here. Myself Kalpita Nath and I am research scholar at IIT Kharagpur. I am here with week 9 of problem solving session of transport phenomena course of NPTEL under the guidance of Professor Sunando Dasgupta of IIT Kharagpur. Okay, so I hope I am audible and visible properly. Okay, so let's proceed to today's session. And I'll be sharing with you the first problem of today's session. This is the first problem of today's session. I hope it's visible on the screen. I'll give you 1 minute to answer this and then I'll tell you the answer because it is a one-line answer only. Okay, so try and answer the question. Okay, so let us first check what will be the answer for this question. So I'll be sharing with you the writing pad. I hope the writing pad is visible. Okay, so question number 1. The Grashoff's number is equal to G beta L cube Ts minus T infinity by V square. Nu square actually. Nu square. Obviously, this is what? This is buoyant force. And this is kinematic viscosity, so this is viscous force. So this will be, answer is option A. Buoyant force upon ratio of buoyant force to viscous force. Okay. Now, let us proceed to question number 2. Okay, so experimental result for local heat transfer coefficient, the local heat transfer coefficient is given. For a flow over a flat plate with extremely rough surface, its relation is given, where A is the coefficient and X is the distance from the leading edge of the plate. Then develop an expression for the ratio of the average heat transfer coefficient, Hx bar, for a plate of length X to the local heat transfer coefficient, Hx at X. Okay, we have to write, we have to find out Hx bar in terms of Hx. That is the average heat transfer coefficient in terms of the local heat transfer coefficient. Okay, so I'll give you 5 minutes to solve this question, as it is a numerical problem, and then we'll go on with the solution. I hope you have solved the question. So, if you have not, I'll go on with the solution. And if you have any doubt, do stop me there and ask me. Okay, the average value of convection heat transfer coefficient over the region 0 to x is hx bar is equal to hx bar x is equal to 1 upon x 0 to x hxx dx. This is the integration from 0 to x upon x. Now, substituting the expression for the local heat transfer coefficient. Okay. hxx is equal to ax to the power minus 0.1 and integrating we obtain hx is equal to 1 upon x 0 to x ax to the power minus 0.1 dx. So we just put it here and it will come as a upon x 0 to x to the power minus 0.1 x dx. Sorry, minus 0.1 dx. It is equal to a by x to the power plus 0.9 upon 0.9. And this comes out to be 1.1 ax to the power minus 0.1. And this is hx again. So hx bar is equal to 1.11 hx. So what comes? This answer comes as A, B. Answer comes as B. Okay. Now let us proceed to question number 3. The diffusivity of a dilute aqueous solution of methanol at 15 degrees Celsius is about 1.28 and 10 to the power minus 5 centimeter square per second. Estimate the approximate value of diffusivity for the same solution at 100 degrees Celsius. Okay, so diffusivity at different temperature at 15 degrees Celsius is given for an aqueous solution, and we have to find out at 100 degrees Celsius. The diffusivity for small concentration of A in B is given by the equation, where Va is the molar volume of solute A as liquid and its normal boiling point and mu is the viscosity of the solution in centipoises. Psi b is the association parameter for the solvent and T is the absolute temperature in Kelvin. For the given solution of methanol, mu at 15 degrees Celsius is given and at 100 degrees Celsius is also given. So we have to find out the diffusivity at 100 degrees Celsius. This you will just find the ratio, and from that ratio you can find out the diffusivity at 100 degrees Celsius. I'll give you 4 minutes to solve this. Okay, so I hope you have solved it, and we'll go on with the solution now. So the equation that is given is known as Filkey-Chang equation. So DAB by this equation is equal to 7.4 into 10 to the power minus 8 root over psi b mb. Okay, one second. MB T mu VA 0.6. This shows that DAB is directly proportional to T by mu. Now T1 is equal to 15 degrees Celsius is equal to 288.15 Kelvin. And T2 is equal to 100 degrees Celsius is equal to 373.15 Kelvin. Now predicted viscosity for a dilute aqueous solution of methanol at T2 is DAB at T2 is equal to DAB mu T1 by mu T2 by T1. 1.28 10 to the power minus 5 centimeter square per second. 1.14 centipoise, 0.2821 centipoise into 373.15 Kelvin by 288.15 Kelvin. So this comes out to be 6.7 into 10 to the power minus 5 centimeter square per second. That is, answer is option B. Okay. Now let us proceed to the next question. Okay. Now consider all the statement, even if one of them is wrong, mark the entire answer as wrong. Otherwise, mark it as true. If the density variation in free convection are due to the temperature variations, only due to the temperature variations, the term may be related to a fluid property known as volumetric thermal expansion. Thermodynamic property of the fluid provides a measure of the amount by which the density changes in response to a change in temperature at constant pressure. Okay, so let us solve it right away. Now, volumetric thermal expansion coefficient provides a measure of the amount by which the density changes in response to a change in pressure at constant temperature or change in density with temperature at constant pressure. So beta is equal to minus 1 by rho del T, P is equal to 1 by rho del P. So obviously this one, what it said that it is only with only to temperature change only due to temperature variations is wrong. So this answer is A, false. Okay, let's proceed to next question. The figure below describes a fluid being enclosed by two large horizontal plates of different temperature where the temperature of the lower plate exceeds that of the upper plate and the density decreases in the direction of gravitational force as shown in the figure. The temperature gradient delta del x is greater than 0 prevails. Which of the following option is correct for the density gradient? Okay, I'll give you 2 minutes for this to answer this. This is a conceptual based question. So you can think a bit about it and then answer me. Okay, so in this case, as we can see that the density decreases in the direction of gravitational force. So the density direct decreases in the direction of gravitational force, thus the density change will be negative. The gradient of density will be negative. As the gradient of density will be negative, del rho del x is less than 0. That is negative. So answer is C. Now let us proceed to question number 6. Okay. Consider all the statement, even if one of them is wrong, then mark the entire answer as wrong, else mark it as true. Each catalyst practice, each catalyst particle is surrounded by a stagnant gas film through which the species A has to diffuse to reach the catalyst surface. At the catalyst surface, we assume that the reaction to A plus B occurs instantaneously, and then the product B diffuses back to the through the gas film to the main turbulence stream composed of A and B. Although the chemical reaction occurs simultaneously at the catalytic surface, the conversion of A to B proceeds at a finite rate because of the diffusion process, which is in series to the reaction process. Hence, we speak of the conversion of A and B as being diffusion controlled. Answer whether it is true or false. Think about it for a minute and then you can answer. Okay, so as we can see, the diffusion process in series with the reaction process. As we speak, the conversion of A to B is diffusion controlled. Okay, and there is stagnant gas film and species A has to diffuse to reach the catalyst surface. As the catalyst surface, the reaction happens and B then diffuses back to the through the gas film. Although the chemical reaction occurs instantaneously. Here the chemical reaction is occurring instantaneously. But at the same time, diffusion will take time. That's why the process is diffusion controlled. So hence answer is A. Species diffusion equation in terms of molar concentration is given. C is total molar concentration, DAB is mass diffusivity, NE is the rate of reaction, rate of increase of mole of species A per unit volume of the mixture, that is the rate of reaction. And C is the molar concentration of A, and X is the mole fraction of species A. For one-dimensional steady-state diffusion in a non-reacting medium, the equation reduces to what? Okay, so here we just have to find out like okay, this conditions are given, so assumptions are already given. In based on that assumption, we have to cut out the terms that we don't require in the main equation. Okay, so I'll give you 4 minutes, 3 minutes in fact to solve this, and then we'll go on with the solution. Okay, so for question number 7, what are the assumptions that are given to us? First is one-dimensional flow, that is mass flow, and second is steady state. One-dimensional means del phi of something is 0 and del z of something is 0. This 0. This is del C A del T is equal to 0. Next is non-reacting medium. This is Na dot is equal to 0. So this whole equation, this equation will reduce 1 by r del r C d A B del r del x A del r plus 1 by r square del phi C d A B del x A del phi del z C d A B del x A del z plus N A dot is equal to del C A del T. So this cancel, everything cancels out, only this becomes the 1 by r del r of r d A B C del x A del r is equal to 0. So this so becomes del r of C D A B R del x A del r. Okay. As we can see from the option, this gives us answer to be option number A. Okay. Okay, so thus now we'll go for question number 8. Question number 8 to 10 is a linked question. So this is the main equation. A reaction 2A to B takes place in a catalytic reactor where the spherical balls are coated with catalytic material. Reaction A diffuses through the gas film surrounded by the catalyst. At the catalyst surface, the reaction takes place instantaneously, is given. After the reaction, the product B diffuses back into the mainstream. So the equations are given. So first question is, what are the assumptions that are needed to be considered in order to determine the molar flux at catalytic surface? The gas film surrounding the catalyst is isothermal. Steady-state conditions will be required, and diffusion of A and B takes place only in Z direction, which are the assumptions. So I'll give you 2 minutes to think about it, and then we'll go on to solve it. Okay, so the assumptions here that we wanted to take is first, the gas film interface is isothermal, that is temperature is same. One, two is steady state. Three is the diffusion taking place only in Z direction. So okay, so what is the combined option that is suitable for this? Is answer is option D, all of the above. Now question number 9. Mention the boundary condition to give a system for determining molar flux at the catalytic surface. Okay, we have to mention the boundary condition. I'll give you 2 minutes for this and then we'll go on to the solution. Okay, first the boundary condition at z is equal to 0, xa is equal to xa naught. This is already given in the figure. This figure. For second boundary condition, we need to see whether the reaction is instantaneous or not. If the reaction is instantaneous, then z is equal to delta, x is equal to 0. If it is slow reaction, then z is equal to delta, NaZ is equal to K1CxA. The rate at which A disappears at the catalyst coated surface is proportional to the concentration of A in the fluid at the interface, as the reaction is instantaneous. So the final boundary conditions are z is equal to 0, x is equal to xa naught, and z is equal to delta, x is equal to 0. So what are the options? Option A, B. Okay, let us proceed to next question. The conversion of A to B is considered as which of the following? Give you. Okay, I'll give you 2 minutes to answer this, and then we'll go on with the solution. Like this is just one line solution, so 1 minute will be sufficient for answering this. Okay, here the chemical reaction may be instantaneous, but and the conversion of A and B, conversion A to B is instantaneous, but uh, the reaction, the total conversion proceed as a finite rate because of the diffusion process, which is in series with the reaction process. Hence, the conversion of A to B is diffusion control. So, answer is A. Question number 2. Now, let us proceed to the next question. Okay. So, the flow of oil in a journal bearing can be approximated as a parallel flow between two large plates with one plate moving and the other being stationary. Okay, so such flows are known as Cauchy flow. Consider two large isothermal plates separated by 2 mm thick oil film. The upper plate moves at a constant velocity of 12 meter per second while the lower plate is stationary. Both plates are maintained at 20 degrees Celsius. Obtain relations for velocity and temperature distribution in the oil. Determine the maximum temperature in the oil and the heat flux from the oil to each plate. I'll give you 5 minutes to solve this question and then we'll go on with the solution. I hope you have solved this. If you have not, then let us proceed with the solution. Okay. First, there is parallel flow of oil between the two plates, and it is considered, and the velocity, temperature distribution, and the maximum temperature and total heat transfer we need to determine. First, let us set the assumptions. First is steady state operating conditions. Then oil is incompressible. Oil is incompressible substance with constant properties. This oil is incompressible and its properties are constant. Body forces such as gravity is negligible. The properties at 20 degrees Celsius is we can find out from the appendix, that is K is 145.145 watt per meter Kelvin and mu is 0.800 kg per meter second. 0.800 Newton second per meter cube. We take x-axis to be the flow direction and y to be the normal direction, and this is a parallel flow between two plates, and thus v is equal to 0. Thus the continuity equation is del u del x plus del v del y is equal to 0. V is 0, so del v del y is 0, so del u del x is equal to 0. That is, u is a function of y only. Therefore, the x-component velocity does not change in the flow direction. That is, the x-component velocity does not change the flow direction. Now, u is a function of y, v is 0, and the pressure gradient del p del x is equal to 0. Flow is maintained by the motion of the upper plate rather than the pressure gradient. Flow is maintained the motion of the upper plate, thus the pressure gradient is considered to be 0. So therefore the x momentum equation, as we wrote the previous day, will be rho u del u del x plus v del y is equal to mu del square u del y square minus del p del x. This is 0. This is 0. U is not a function of x. So therefore mu, that is del square u del y square is equal to 0. Now integrating, u is equal to c1 y plus c2. Now the fluid velocity at the plane surface must be equal to the velocities of the plates because of the no slip condition. Therefore the boundary conditions are u at 0 is equal to 0 and u at L is equal to v. U at 0 is equal to v. Right, then the frictional heating due to the viscous dissipation in the case is significant because of the high viscosity of N and large plate velocity. The plates are isothermal and there is no change in the flow direction, and thus the temperature depends on Y only. Also, u is a function of temperature, is a function of y, is a function of y only, and v is equal to 0. Thus, the energy equation with dissipation reduces to, the energy equation will reduce to k del square t del y square plus mu del u del y square. K del square t del y square is equal to minus mu v by L whole square. Del u del y is equal to v by L. Del u del y is equal to v by L. Okay. Cos del del is equal to v by যেহেতু u is equal to y by L into v. Now, dividing both sides by k and integrating twice, we get ty is equal to minus mu by 2k y by L v whole square plus c3y plus c4. Now, the boundary condition for temperature T at 0 is 0 and T at L is equal to T0. Given the temperature distribution to be Ty is equal to T0 plus mu v square by 2k y by L minus y square by L square. Temperature gradient is defined now. Temperature gradient is determined by differentiating Ty with respect to y. That is Ty with respect to y del y. So that gives mu v square by 2kl 1 minus 2y by L. Okay, so the maximum the location of maximum temperature is determined by settling this is equal to 0. This gives just 0 and solving for y. So y gives L by 2. How? Dt dy is equal to mu v square by 2kl 1 minus 2y by L is equal to 0. Just differentiated it. So this gives y is equal to L by 2. Therefore, the maximum temperature will occur at mid-plane, which is not surprising since both the plates are maintaining the same temperature. So the maximum temperature occurs at y is equal to L by 2. Now, what is the maximum temperature? Just put L is equal to, y is equal to L by 2. This gives T naught mu v square by 2k L by 2 by L minus L by 2 whole square by square. T naught plus mu v square by 8k. This gives 20 plus 0.8 Newton second per meter square. 12 meter per second whole square. 8 8.145 watt per meter degree Celsius. This into 1 watt, 1 Newton meter per second. This gives 119 degrees Celsius. Now from this you can find out the heat flux. Okay, so for finding out the heat flux, I'll take 2 minutes for you to solve for heat flux, and then we'll go for the solution of heat flux. Okay, now let us solve for the heat flux. So the heat flux Q naught is equal to minus K dt dy at y is equal to 0. Minus K dt dy we already found out. This will be mu v square by 2kl 1 minus 0. Y is equal to 0, we'll put 1 minus 0. So this will be minus mu v square by 2l. So this is 0.8 Newton second per meter square, 12 meter per second whole square by 2 into 0.002 meter. 1 watt, 1 Newton meter per second. 28800 watt per meter square minus. So heat flux is equal to at L. At 0 it is this. At L it will be minus K dt dy at y is equal to L minus K mu v square by 2kl 1 minus 2 mu v square by 2l is equal to minus q naught 28800 watt per meter square. Now the heat flux at two plates are equal in magnitude but opposites in sign. A temperature rise of 99 degrees Celsius confirms our suspicion that the viscous dissipation is very significant. Also, the heat flux is equivalent to the rate of mechanical energy dissipation. Therefore, the mechanical energy is being converted to thermal energy at a rate of 57.2 kilowatt per meter square of plate and area to overcome friction in the oil. Finally, the calculations are done using oil properties at 20 degrees Celsius, but the oil temperature turned out to be much higher. Therefore, knowing the strong dependence of viscosity on temperature, the calculation should be repeated using the properties of the average temperature of 70 degrees Celsius to improve accuracy. It can be repeated as such. Let us proceed to the next question now. A 2 meter, 3 meter flat plate is suspended in a room. Okay, this is 3 meter and this is 2 meter. This portion is 2 meter and is subjected to air flow parallel to it surface along with 3 meter long side. Along its 3 meter long side, the free stream temperature and velocity of air are 20 degrees Celsius and 7 meter per second. The total drag force acting on the plate is measured to be 0.86 Newton. Determine the average convection heat transfer coefficient for the plate. Let us take 10 minutes to solve it and then we'll go on for the solution. So it's said that a 2 meter by 3 meter flat plate is suspended in a room and is subjected to airflow parallel to its surface along its 3 meter long side. The free stream temperature and velocity are given as 20 degrees Celsius and 7 meters per second, respectively. The total drag force acting on the plate is measured to be 0.86 Newton. Now we need to determine the average convection heat transfer coefficient for the plate. Okay, so first we need to determine the assumptions that we need to keep. First one, steady operating conditions exist. Second, the edge effect are negligible. Third, the local atmospheric pressure is 1 atmosphere. The properties given is density is 1.204 kg per meter cube. Cp is given 1.007 kilojoule per kg Kelvin and Prandtl number is 0.7309. Okay, now the flow is along 3 meter side of the plate and thus the characteristic length L is 3 meter. Both sides of the plate are exposed to airflow and thus the total surface area 2WL is equal to 2 into 2 meter into 3 meter is equal to 12 meter square. For flat plates, the drag force is equivalent to friction force. Okay. The average friction coefficient CF can be determined as CF is equal to friction force upon area rho V square by 2. Okay. So Solving for CF, this is 0.86 Newton, 1.204 kg per meter cube density. Area is 12 meter square. Velocity is 7 meter per second whole square into 2. Okay. Upon this upon 2. And this into 1 kg meter per second square upon 1 Newton. So this gives to be 0.00243. Okay, this is the average friction coefficient. And now the average heat transfer coefficient can be calculated from the modified Reynolds analogy. So modified Reynolds analogy says that CF H is equal to CF by 2 rho V Cp by Prandtl number to the power 2 by 3. So 0.00243 upon 2, 1.204 kg per meter cube, 7 meter per second, 1007 joule per okay joule per kg degree Celsius upon 0.7309 2 by 3 whole to the power 2 by 3. 12.7, this is 12.7 watt per meter square degree Celsius. This is the heat transfer coefficient. This is the average heat transfer coefficient. Okay, so this is all about today's problem session. I hope you all have understood everything, and if you have not, then you can mail me up. Thank you for being here. I'm ending the class today.